Hey guys, this is Kerry, and this is the answer key video for homework number 2 from Unit 3. Alright, so simplify each of the following until you have x to a single power. X to the 4th times x to the 3rd. That's x to the 7th. And like we talked about in class, you want to have both proofs in your head. One proof is you're supposed to add the exponents, so that works. Another proof is x to the 4th is 4x's being multiplied. And then x to the 3rd is 3x's being multiplied, and really that's just 7x's being multiplied for x to the 7th. For the next one, x to the 4th to the 3rd, first off, power of a power, we multiply the exponents, we get x to the 12th. But then we could do a similar proof to what we did before, where we could say x to the 4th to the 3rd means that you've got x to the 4th times x to the 4th times x to the 4th. So you have x to the 4 plus 4 plus 4, which is 12. So both proofs are useful to have in your mind. Now the next one, write the following expression with a single radical and a single power, seems totally different from these two. But you have that moment of mathematical insight, and you realize x to the 4th with the 3rd root is really x to the 4 over 3 power. Because when you have a fractional exponent, the number on the bottom tells you the root, and the number on top tells you the power. So, because we have these observations, we can also do the same thing to the next one. So this one right here is x to the power of 2, root of 5. And now when we multiply this and this, it looks a lot like part A. So because we're multiplying two things with the same base, we add the exponents, x to the 4 over 3 plus 2 over 5. And to add these fractions, we have to get a common denominator. So we multiply this one by 5 in the numerator and denominator, and this one by 3 in the numerator and denominator, and we get x to the 20 over 15 plus 6 over 15, x to the 26 over 15. But they want this as a single radical and a single power, so we are not done. We need to convert this back. So it's the 15th root of x to the 26th power. Very cool. Complete each of the following. Okay, well, this one's really similar to what we just did. X to the 3rd times x to the 5th, that's x to the 8th. X to the 15th, x to the 8th times x to the 3rd, x to the 11th. Hopefully you did that really fast. Completely factor each of the following expressions. So factoring with these, we've only learned one method so far. That's going to be the greatest common factor method. And in order to use this method, we're looking for the greatest factor that the two numbers, or three numbers, all share in common. So with these, we're looking for a number that divides 18 and negative 27. The biggest number that does that is not 3, but 9. So sometimes you have to take a couple of tries. 9 goes into 18, 9 goes into 27. So we get 9 times 2x minus, what times 9 would give us, negative 3. For the next one, we have 15b to the 9th plus 12b to the 4th. Now this one is different from the last because we're looking for a number that divides 15 and 12, the biggest number that does, and that would be 3. But we're also looking for how many b's this term and this term share in common. So since they share b to the 4th in common, this gives us 5b, so 3 times 5 is 15. b to the 4th, we factor that out, we're left with 5 b's, b to the 5th. And then for the next one, we have a 4 here, and if we factor out this b to the 4th, we're not left with any b's from that term right there. Next up for part C, we're looking for the greatest common factor for all three of these terms. So that's going to be a number that divides all three of these, which would be 3. And then what power of x do they all share in common? Well, they all have at least x to the 5th, so we'll factor out x to the 5th. That gives us 8. 3 times 8 is 24. X to the 5th times x to the 5th is x to the 10th, plus 3 times 6 is 18. If we factor out 5 x's, that leaves us with x to the 3rd. 3 times 7 is 21. And if we factor out 5 x's, we're not left with any x's there. And so we're done using GCF there. All right, so for the next one, we're only going to do the last one. I'm going to let you guys do 5 on your own. 5 is very similar to 6, but easier. So let's do the more difficult one. Solve the following equation for x in terms of a, b, and c. So we want to solve for x. The first thing, I don't like that fraction with x in the denominator, so we'll multiply by x on both sides. That gives us ax plus b equals cx. Now since we want to solve for x, maybe we should move all of the x terms to one side and all of the non-x terms to the other side. So let's do that by subtracting cx from both sides. And then to cancel out this b and move this b to the other side, we should subtract b from both sides. So b minus b cancels out, cx minus cx cancels out, and that gives us ax minus cx equals negative b. Now, this is a lot better than the equation that we started with, because we have both x terms on the same side. But we still can't solve for x, because we need to have just a single x. So the moment of insight that we have here is, because this term and this term have x in common, we could use the greatest common factoring method to factor out that x. Now x times a would give us ax, and x times negative c would give us negative cx. Now this is the best equation we've seen so far to solve this problem, because we have just a single x there. So in order to get rid of times a minus c, we have to divide by a minus c on both sides of the equation. This gives us x equals negative b over a minus c. Alright guys, you can use a similar technique to solve this problem here, but this is going to be a challenge for you to do, so figure it out.